If you click this video away, please tell me what the reason was so that I can improve. Otherwise, hi and welcome. I'm trying to learn physics. Today, how light behaves. And after we've done that, we're going to do body center training. And if you participate in the body center training, then it's at your own risk. And this is part 3 to how light behaves. Now we're going to go on here with light in modern physics and trying to understand it. Light in modern physics. The wave theory works well in many ways, as does the ray theory in the field of optics. The wave theory is that wave moves as a wave, not in a straight line, but as a wave. And that is possible by having the light, just out of something at talk, it goes into all directions. But if you have a piece of paper with a very thin hole, it goes then only through that hole, the light which goes through it, goes then on in a straight line. I don't know, was it for the waves? For the waves, that was also the explanation with the shadows. The shadow is not clear, but with some are going a bit to the side. And the thing with the ray, I did not understand. It was something like that. We're talking about a subject-like subject. But as a description of the nature of light, it too has shortcomings. One of the first problems to trouble 19th century physicists was the question of what it is that waves. Okay, what in the light is waving? The photons are the light, they are transporting the light, or they are the light, but what is now waving in the photons is the big question. Ripples on water and sound waves both consist of disturbance which travels through a medium, water and air respectively. When water is moving, the water itself is not moving, it is just the force moving on, something like that. So the water itself of a wave is not moving on, it is the force of the wave moving on. It's not the whole water transported forward. But where it is water transporting it, and by air, by sound, where is the air transporting the sound? And that makes sense that there are no waves, or at least is it explained. But the question is, what is now doing the waves when it is about light? Light, however, can travel in empty space. So, no air for the sound or water for the water waves. Light can travel in empty space, which can hardly be thought of as a medium at all. Nevertheless, physicists postulated the existence of an all-pervasive medium called luminiferous error, and having done so, they tried to detect it. Okay, they said there has to be a medium. What we think is empty is actually luminiferous error. They had a name for it, and they tried to find what they said we're going to find, what they postulated. They failed. The most noted failure of all being the Michelson-Morley experiment, which paved the way for Albert Einstein's theory of relativity. Okay, they failed to find a medium through which light is transported. They failed to find in the atmosphere on the Earth there is air, but otherwise in the universe there is oftentimes nothing. And they failed to prove that there is this luminiferous error. But one of these failures, this Michelson-Morley experiment failure, was important for Albert Einstein's theory to relativity. It is now recognized that light is an electromagnetic phenomenon which does not require a medium to transmit it. Okay, light is a part of the electromagnetic force, or of the electromagnetic things. It does not need anything. Now, in the last part we had it, and the whole thing of electromagnetic rays, I think, they are the ones visible for the human eye, basically in the middle. They had a length of a million of meter. And there are now the radio waves, they are kilometers long, and then the gamma rays on the other side of the big spectrum with the light in the middle, they are a million of a million of meter or something long. So we get shorter. And light is in the middle with a million of a meter of length. The waves of the light itself. The study of the way radiation, both visible and invisible, is emitted and absorbed, led to further modifications of the wave theory. A hot body emits radiation of many different wavelengths. When it is at a temperature of about 100 degrees Celsius to 200 degrees Celsius, it emits mainly infrared radiation, which can be felt as radiant heat. There are different forms of radiation. One form is light. Now we're having another one, the infrared long wavelength radiation. And that can be felt as heat. So light is here felt as heat. But all makes more and more sense. It all belongs together. All these different things, I think. What is not thermal radiation? It has to be somewhere in between, somewhere between infrared and light. Because what is not warm at the sun? So we're puzzling here something together. We found just in the last part out that light is part of the electro waves, or whatever, of these things. It was on that. We're going to find it again. Light is just a part of it all. So gamma rays are radio waves, and gamma rays and light is just a thing on the whole spectrum. They have just different types of length. And now we're having here infrared. It is hot heat of something which has 100 degrees Celsius. And that is also part on that whole spectrum. At a temperature of about 600 degrees Celsius, it begins to glow a dull red. And as the temperatures increase, it glows more brightly and produces radiation with shorter wavelengths. So it emits different light in different wavelengths the more hotter it gets, the thing which we have hot. But it's interesting. So you have, the more you heat it, when the color changes, it glows stronger. But that just that it gets hotter makes it have a different type of light. But it's interesting. It seems logically something which burns or glows differently has a different color, but if you think about it, just because it gets hotter, it has a different light. I think it may be also possible that if you have a piece of wood or something, that also the thing which is not burning in the wood is something else if the temperature is differently. But at about 600 degrees Celsius, it begins to glow a dull red, and as the temperature increases, it glows more brightly and produces radiation with shorter wavelengths. A simple theory of radiation emission suggests that any body, whether hot or not, should emit more short waves than long, simply because more complete waves of short wavelength will fit into a given space than the those of long wavelength. However, this deduction does not accord with observation. Nothing less than a scientific revolution was required to resolve this discrepancy, and this was provided by the German physicist Max Planck in 1900. Okay, I don't really know what it was now. So we fought for a time with things that it is more likely that things with shorter wavelength are emitted, so more gamma rays or light or something, because because it is just easier to have more different waves in the same space than long waves. But that seems to be not true. Energy in photons. Max Planck postulated that a light wave cannot carry energy smoothly and consistently, but only in separate amounts which depend on its wavelength. These packets of energy are called photons. The shortest wavelengths have photons of the highest energies, and so at low temperatures there is not enough energy available to excite them. Only long wavelengths can be radiated. As a body gets hotter, however, it can emit photons of shorter and shorter wavelengths, as well as more photons altogether, which is just what is observed. If something glows or burns, it can emit a lot of light and also more brighter light at the same time. So what is it? As the body gets hotter, however, it can emit photons of shorter. So shorter means brighter. Shorter means brighter. We had here visible light has a wavelength of over 7-10 millionths of a meter for red light and about a half for blue. Red is 0.7 and blue is 0.3 millionth meter long. So what is the longer? One with 0.7. So red is longer, but red seems more brighter. Okay, let's go. We're going to find it out later. Radiation, therefore, exhibits two apparently contradictory features. When it passes through space, it behaves as a wave, and interferes and diffracts just as a wave should. Okay, if you're having radiation, I think that includes now normal light. And if it moves now through free space, when it is as a wave moving, and it is also diffracting, that means, I don't really know what it means. I don't really know what the word means. It is diffracting something else, or is it diffracted? When it is emitted or absorbed, however, it behaves more like a stream of particles, each of fixed energy, which depends on the wavelength. This dual nature is known as complementarity. Okay, the energy that these photons have has to do with the wavelength. I would now guess the shorter, the higher the energy. Because we had here, only long wavelengths can be radiated. As the body gets hotter, however, it can emit photons of shorter and shorter wavelengths, as well as more photons altogether. The shortest wavelengths have photons of the highest energy. So the shorter the higher the energy. That makes sense. But they are not traveling faster. That is interesting. Because if you take a water wave, the smaller the wave, you would say it has the less energy. But that is about the mass, and light has no mass. Photons have no mass. Okay, light is traveling as a stream, as a wave through space, but when it comes to something, it just goes into it as one stream with a fixed energy depending on what type of wavelength it had. But shorter would be in that direction. If I have here the radio with the kilometers long waves. Okay, we're going to continue in the next part with the basic properties of light and the proof that light travels in waves. And we're going to come back to the whole text. But for now, that was the physics part to how does light behave. How light behaves. If you were here for physics, you can go directly to the next part of physics. If you stay here and participate in the body center training, when is the leg we're having the legs standing hip width apart, we're going a bit down into the knees, and we're flexing the leg muscles, and we're pressing the legs together, And now, bend one leg, straighten the leg, and bend it again, press together, flex, and unbend it. So we over, straighten the leg, and whole time flexing and pressing together, and now bend the leg again, press together, flex. Next exercise, wider apart, a bit down into the knees, flex the muscles and press together, and now straighten again with one leg, and bend it again. Other leg, straighten, and bend again, press together, flex, and up. A bit closer together, and press to the outside. One leg up, right angle with the leg, flexed foot, even line hips, tall up with the back, and press on the top against the knee with a little bend in the elbow. And press from the inside. Now press up and the side. And now press from the outside and outside. And close inside. Other leg up. Press from the top. Same setup. Press on the side. Press up to the side. And press on the outside and out slowly. And close again. And now 3 exercises on the ground. First, a side plank, just on your elbow. You can do it also on the knees. Now if you like, one leg up. Now, same on the long arm. First standing. An arm out and leg up if you can. And bring elbow to knee. And on the other side. First on the elbow. One leg up. And now on the long arm. Arm out and leg up and pull knee to elbow. And up again. Do the walk a bit on the place. Pull one leg up, the other one. Take the leg at the ankle, straight back, knee down. Other leg, straight back, knee down. Legs wide apart, breathe in out on. Breathe again out. Breathe in and close the legs. And breathe again out. Head goes back. Body center stretching. Thank you very much. And next time.